Pythagorean Theorem has inspired hundreds of proofs. Each one is like a unique piece of art crafted from the palette of mathematics. Most of the proofs aim for simplicity and elegance. The definition of brilliance varies by context, but usually involves something exceptionally clever or talented, something that's outstanding or excellent. In my mind, the three proofs we cover all qualify as brilliant. In this video, we focus on the simple proof, which has been labeled the shortest proof yet. As you watch this video, I encourage you to imagine what it would feel like to be the first to discover this proof and the series of aha moments. I did, and quite honestly, it has been exhilarating, and I invite you to experience the same thrill. Our journey starts with the general formula of the Pythagorean theorem. Given two sides of a right triangle with lengths a and b, the relationship to the hypotenuse c is beautifully simple. A squared plus b squared equals c squared. In our diagrams, big A will always face side little a, and we will always use that convention. The most famous triangle is a equals 4 and b equals 3, and we can throw these numbers into the formula and instantly we identify the hypotenuse is root 25, which is 5. We can measure this fact for this one triangle, but how do we prove this relationship works for every right triangle? Every right triangle seems impossible because there literally are an infinite number of these triangles. But math can conquer the infinite. The xy coordinate system is the perfect landscape for a right triangle, where side A rises on the y-axis and then side B stretches along the x-axis, and they meet at the origin. Math requires being creative, so imagine you and me tinkering with a right triangle, geeking out a bit, armed with a protractor and eager to delve deeper, where we are not content with this static triangle that does not move. Hoping to make our mark, we draw a line from point C to the hypotenuse, not just any line, but a perpendicular line that intersects at a crucial point we will call P. With that, we revealed a mesmerizing yet hidden symmetry. We unveil what's hidden by identifying that within our original triangle, we have created two new triangles, red and green. In our 3, 4, 5 triangle example, the angle at B is approximately 37 degrees and the angle at A is 53 degrees. And notice that angle A and B must sum to 90 degrees since we already have a 90-degree right angle and a triangle's three angles sum to 180 degrees. The key point here is that these smaller red and green triangles share the 37 and 53 degree angles with each other and the original large triangle. And this reveals that they are similar, which means proportionate in shape, just different in size. Now, this is not a quirk of specific triangles. It's a universal truth that applies to all right triangles when we create our perpendicular segment. Define the angle at B as alpha, and the dance of angles and sides unfolds predictably, with all triangles maintaining this relational symmetry. This universal truth may appear to be just a fact, but it is packed with power. Our dramatic scene defines A, B, and C to represent the sides for any right triangle. Each right triangle has a perpendicular P, which creates three triangles, red, green, and big ABC. The infinite is indeed large, but we are set up for success because we also know that our angle relationships apply to each of the infinite collections of right triangles. The consistent creation of similar triangles, regardless of side length, means their corresponding sides remain proportional. What does this mean in practical terms? Rotate the red and green triangles to align with the large triangle, and a common ratio emerges. Can we quantify this ratio? Warning, what you're about to consume may seem like algebra. Start with the large triangle where B is the short side and C is the hypotenuse, and create the ratio of short side to hypotenuse as B over C. For the green triangle, its short leg is part of the large triangle's hypotenuse. Now, we do not know this length, so define it as C1. The hypotenuse is opposite the right angle, labeled B, and this forms a ratio C1 over B for the green triangle. The secret sauce is because these triangles are similar, we can equate the ratios, producing B over C equals C1 over B. Think of this as like a mirrored equation that reflects their similar structure. Let's box it because we want to recycle this formula. Next, our second ratio is the large triangle to the red triangle, where we compare the long side to hypotenuse. For the large triangle, the ratio is A over C. For triangle red, the longer leg is the segment from point B to P, which is C minus C1. This produces a long over hypotenuse ratio as C minus C1 all over A. Now, algebra completely takes over and reveals the magic. Take the box red equation and cross-multiply to isolate A squared. And likewise, take the box green equation, cross-multiply to isolate B squared. We quickly arrive by simply summing the two equations and simplify to produce the formula that has stood the test of time. A squared plus B squared equals C squared. We are done barely after we started. Isn't it cool that we use geometry to create equations, but then let algebra do its thing? One big idea going on here is that even though algebra and geometry seem like two separate subjects, they work together, like they're talking to each other. Okay, we could quit, but there's something too beautiful going on, and this beauty is based on understanding the ratios between triangles. We raced through the algebra, but let's bring geometry up to speed. We know the ratio between red to the large triangle is A over C. The ratio between green to the large triangle is B over C. This also creates the ratio between the red and green triangles as A over B. Of course, we could substitute A equals 4 and B equals 3 for this one triangle, but think bigger than 1. Imagine an infinite number of right triangles. Now, think deeper than facts and formulas and create a dynamic picture in your mind. We just discovered that not only do we always create similar right triangles with our perpendicular segment, but the lengths of the sides define what that ratio or proportion is, and it is so simple, and this relationship is true for any right triangle. One thing I appreciate about this proof is it reveals how geometry and algebra are not two independent subjects, but highly connected, where each step, each ratio, each alignment is more than just a calculation. It's a glimpse into the elegant architecture of math itself. This proof is not just about knowing the operations, but understanding the profound relationships that define all right triangles. In a sense, it offers a window into the fundamental nature of shapes and numbers. This is a good start. Our next proof is the classic work from Euclid. To be honest, I struggled through this proof, so I created a separate video to highlight one key concept, which is the focus in our next video. But before we leave, there are so many fascinating things I'm leaving out of this video that I'm saving for part 2. However, I'll plant some seeds by posing 2 questions for you to consider. The first is, in our proof, we did not calculate the length of segment CP. How can we calculate the length of this crucial segment based on what we learned and crunch it with ease? And the second question is, if we double the sides of our original triangle so the side lengths are 6 and 8 rather than 3 and 4, how do we know the hypotenuse doubles from 5 to 10 without plugging it into our formula? This may seem logical, but why? How could you convince a skeptic this is true? We will also uncover some beautiful relationships in part 2. Here's a quick animation of what is to come, where the abstract becomes tangible and the mathematical becomes magical. Enjoy.